Last week we saw how we could solve second-order homogeneous linear differential equations, most of which had constant coefficients. We'll explore that in more detail as we go through. One of the key ideas from that, though, which was due to the linearity of the equations, is that we could combine the solutions as linear combinations as well. So when we had a second-order equation which had y double prime plus y prime and y, and maybe some coefficients out front, this would have been the standard form for a second-order differential equation that's linear. Then if we had two solutions, y1 and y2, then because this was linear, we could guarantee that the general solution, which had y1 and y2 in it, some constant multiplier for y1, some constant multiplier for y2, that would also be a solution. And for those who have a little more experience with linear algebra, we could say that those functions, y1, y2, are a basis for a vector space, and the general solutions would be a vector space. If you're not as familiar with linear algebra, don't sweat it. Just know that how you can construct the general solution from building blocks of simpler solutions. If we further zoomed in and focused our attention on differential equations with constant coefficients, so instead of p of x and q of x, we actually had single scalar values in front of the derivatives and the y function, then what we could do is make an assumption. We would assume that our solutions look like an exponential. And that's a natural assumption to make, even though it might not be obvious at first glance, because the idea is somehow y and its derivatives have to add up and cancel out and get zero. Well, a natural way for that to happen would be to use an exponential, because the derivative and the second derivative would then also be exponentials. If we'd used other functions like polynomials, well, if we take a derivative of a polynomial, we lose a power. Things might not cancel out quite as easily. In terms of process, that assumption led every single time to this next stage. When we plug in y equals e to the rt, we always got y prime was equal to r e to the rt, and y double prime was r squared e to the rt. What that led to, when we subbed in at each of these values, was an e to the rt times all of this, but the e to the rt, if we have it equal to 0, can get cancelled away, and we ended up with what we called the characteristic equation for this differential equation. Same coefficients, but every derivative of y turned into a power of r. Second derivative of y gave us r to the power 2. No derivative of y gave us r to the power 0, or just 1 for this last term. And that was a great gateway. What it gave us was a method for working from the differential equation, complicated, has derivatives, to this form here, which is simple and algebraic. There's no derivatives here. This is just a regular equation that we can solve any way we like. Once we had the solutions, we would sub the r back into the y equals e to the rt. Now there were some wrinkles with that last step, and we'll talk further about those, but in principle that was the approach that we found successful in every case for this kind of differential equation. Even better, what we saw for order 2 can also be applied to order n, so higher derivatives. If we had a fourth derivative, a 10th derivative, turns out it doesn't matter. The key thing is that we have a linear equation, so notice we have our y's here, and they're simply being multiplied by factors that only involve x. Just as a notational thing, this y with the parentheses around the n is equivalent to the nth derivative of y with respect to x, in this case here. And it's just a short form, so we don't have to write y prime 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 prime, because that gets a little awkward pretty quickly. So we use this or this notation instead. Now, any equation that has nth order derivatives and is linear, we can obviously divide through by that leading coefficient, as long as it's not 0, and we would get a new form of the equation, which would have a leading 1. That would be the standard form, plus some other functions out front that could be any form at all, and this part here would be non-homogeneous. We'll explore that further a little later in the course. Or homogeneous if g equals 0. If this function was just a 0, that would be our homogeneous case. And so we ask ourselves, with this nth order scenario, how do we go about solving it? Well, it turns out that instead of a span of 2 linearly independent solutions, if we have an nth order derivative, then we're going to have n linearly independent solutions as our basis, and we can build a general solution from that. Now, we've just added a complication to our lives because we've added this key phrase, linearly independent, to these solutions. So these solutions somehow have to be different enough from each other to make an interesting set so that we can't combine them and cancel them out. And what that means is we'd better have a test for linear independence for larger sets of functions. Fortunately, as it turns out, the method we had for classifying whether 2 functions were linearly independent or not works just as well or generalizes nicely to a set of any number of functions. Yes, we're going to go back to that idea of the Wronskian from a previous lecture.